Yeah. Hello and welcome to our presentation on enhancing consistent ground maneuverability by robot adaptation to complex off-road terrains. This work was done as a collaboration between the Colorado School of Mines and the United States Army Research Lab. So in this research, we addressed the problem of enhancing consistent ground maneuverability, which enables the robot's actual behaviors to accurately match its expected behaviors, while also adapting to a variety of complex unstructured off-road terrains. As can be seen from the motivational videos, this is a common problem in real-world everyday navigational terrains. The challenge we aim to address is the inconsistency caused due to setbacks. Setbacks can be defined as the factors that increase the difficulty of a ground robot to achieve its expected behaviors. Example setbacks would include wheel slip, reduced tire pressure, heavy payload, etc. Furthermore, when robots are navigating over off-road forest environments, it's challenging for a robot to model all the unstructured nature of these terrains, as these terrains exhibit a wide variety of characteristics, including changing terrain types and slopes that cannot be modeled in a robot beforehand. We then develop an approach that enables in robots the ability to generate consistent navigational behaviors. Our approach learns offset behaviors that allows the robot to compensate for the inconsistency between the actual and its expected behaviors, without the need to explicitly model the various setbacks, while also adaptively navigating over the changing terrain types. In addition, our approach is also able to integrate multimodal terrain features to characterize various terrains and estimates the importance of features to improve robustness of the terrain adaptation. This is all implemented in a unified regularized optimization framework with a theoretical convergence guarantee. The key novelty of our approach is the introduction of a novel mathematical formulation to generate consistent navigational behaviors by learning offset behaviors. We also introduce a new regularization term to learn important terrain features from multisensory robot observations and fuse them together to improve the robustness of robot adaptation to unstructured terrains. We then propose a novel optimization algorithm to address the formulated regularized optimization problem with dependent variables and non-smooth regularization terms. Our optimization algorithm holds a theoretical guarantee to converge to a global optimal solution. And as an experimental contribution, we provide a comprehensive performance evaluation of learning-based terrain adaptation methods on a physical robot over a wide variety of individual and complex unstructured off-road terrains. We first formulate the problem of learning to generate consistent navigational behaviors using a regularized form optimization framework, which is parameterized by two different weight tensors. Our approach includes four variables. The first one is the terrain feature tensor, which contains multimodal terrain features from a sequence of multisensory robot observations. We then have a second variable, which is the expected robot behavior, which is used to represent the behaviors that the robot is asked to execute. However, due to setbacks in the terrain, this behavior cannot be executed accurately. And the resulting behavior is the actual robot behaviors that we see indirectly using SLAM methods. Finally, the fourth variable to our approach is a behavior difference tensor, which is used to store the difference between the robot's actual behaviors as well as the expected behaviors. Out of the two parameters, the first parameter is the weight tensor W, which we use to learn navigational behaviors from terrain features. And the second weight tensor U is used to learn offset behaviors from the behavior differences tensor. Then we formulate the problem of generating consistent behaviors as a regularized optimization problem with the weight tensors W and U as its parameter. And in our formulation, we aim to optimize these weight tensors. In our formulation, the first term in our equation is a loss function that is used to represent the error of modeling the actual behaviors using a combination of both robots' terrain features as well as its behavior differences. The second term is a regularization term, which is used to find the discriminative terrain features towards generating robot navigational behaviors. And finally, the second regularization term is used to find the discriminative time steps from a history of sequence of observations towards generating adaptive behaviors. with lambda 1 and lambda 2 in our approach as being the trade-off hyperparameters which are used to control the amount of regularization. Then for any given time with robot terrain observations and behavior differences, consistent navigational behaviors are estimated using the following equation, with the first term in the equation denoting the expected behaviors that are learned and the second term denoting the offset behaviors. To validate our approach, we use a clear path Husky unmanned ground vehicle and perform two sets of experiments. The first experiment includes the Husky robot navigating over individual types of terrains, and the second experiment includes the Husky robot navigating over complex unstructured off-road terrains. And for both these experiments, the robot autonomously navigates from one point to another while adapting its navigational behaviors over the different terrains. And we implement our approach as a local controller that acts under a local planner to generate navigational behaviors and goes from one point to a goal position that the robot is given. We compare our method using with three different baseline approaches. The first method is learning from demonstration approach, where an expert human gives expert demonstration to robot for navigating over various terrain. The second method is multimodal learning from demonstration, in where the expert is the human, and then we use multimodal terrain features to learn as a representation learning method. The third method is the terrain apprenticeship and terrain representation and apprenticeship learning, which uses joint terrain representation and apprenticeship learning to perform terrain adaptation. We use the evaluation metrics of failure rate, traversal time, and inconsistency to compare the different methods, with failure rate indicating the number of times the robot fails to complete the navigational task. The traversal time being the time taken to complete the navigational task in all of the successful runs. And the inconsistency is the actual error between the robot's expected behaviors and actual error in terms of the robot's poses. For the two sets of experiments we use to validate our approach, the first set of experiment includes navigating over individual types of terrains. In this experiment, all the methods are trained and tested over 5 different individual off-road terrain tracks, including grass track, sand track, gravel terrain, a medium rocks terrain, and a large rock terrain. And during testing, no online learning is performed to perform on-the-fly adaptation. The second set of experiments includes navigating over 4 different types of complex unstructured off-road terrain types, including grass to medium rock transition, a grass to a large rock transition, the mixed terrain type 1, which is a combination of grass, gravel, sand, as well as rocks. And then there's a mixed terrain type 2, which is a forest terrain. In this experiment, no additional training is performed, and we use this experiment to show the ability of ground robots to generate consistent behaviors in unfamiliar and unseen environment. Shown here is a video where we compare the methods over large rock terrain. We observe that our method, all the methods except the learning from demonstration approach, are able to successfully navigate to a goal position, whereas the learning from demonstration approach encounters significant wheel slip and is not able to reach the final goal position. In the mixed terrain type 1, which is a combination of sand, grass, rocks, and gravels, we observe that both learning from demonstration and multimodal learning from demonstration approaches get high-centered in the terrain, and both the TRL approach and our approach are able to successfully navigate to the goal position given to the robot. In this video, we show the mixed terrain type 2, which is the forest terrain. We observe that all the methods, except our approach, they fail to reach the goal position with either colliding with the trees in the forest environment or getting stuck in the branches of the trees, whereas our approach is able to successfully navigate to the goal position. And finally, we also present a scenario where we see that all the methods actually fail in this grass to large rock transition, where specifically the failure occurs whenever the robot is trying to transition from the grass to the large rock kind of terrain. For the quantitative results, evaluation of all the methods are performed based on 10 trials over each type of terrain. So For simple individual terrain types, such as grass and gravels, all the methods allow the robot to successfully traverse over the terrain. However, for more challenging terrain, especially the large rock, we see that both the learning from demonstration and multimodal learning from demonstration approaches have a high failure rate, whereas the TRL approach and our approach have a low failure rate. Our approach, however, has only one failure rate in the large rock terrain and outperform the comparison methods. In terms of traversal time, it is observed that all methods have a similar traversal time in successful runs, but both learning from demonstration methods show lesser traversal time compared to other methods of rocky terrain, suggesting that they try to traverse over this terrain as fast as possible, which is the main reason why they encounter a higher failure rate. Thus, the higher emphasis on high-speed traversal used by these learning from demonstration methods produces an unreliable system where the robot traverses whenever the robot traverses unstructured off-road terrain. We also observe that both the learning from demonstration approach and multimodal learning from demonstration approach do not perform well and have higher inconsistency value over the individual type of terrains, especially over large rock terrain type, suggesting that their actual behaviors are not actually matching with its expected behaviors. We also observe that the TRL has a lower inconsistency and performs the best in the grass rock terrain, but our approach is able to outperform all the previous approaches and obtains the lowest average inconsistency value. When observing the results over navigating over complex unstructured off-road terrain types, each of these methods have a higher failure rate in general, especially over the grass to large rock transition and the mixed terrain type 2. Our approach significantly performs the learning from demonstration approaches in terms of failure rate. And similar to the first set of experiments, we observed that both learning from demonstration approaches have a lower traversal time, suggesting they have higher traversal speed, which in turn lead to a higher failure rate. Moreover, we also see that the learning from demonstration approaches are outperformed by our approach in terms of inconsistency, which with the multimodal learning from demonstration approach performing the worst. So this result suggests that the robots need the essential ability to adapt with the terrains, then only they can reduce the failure rates whenever they are traversing in unstructured off-road real-world terrains. In summary, we introduce a novel method for enhancing consistent ground maneuverability, which advances the state-of-the-art by enabling ground robots' actual behaviors to accurately match its expected behaviors, while also adapting to a variety of complex off-road unstructured field environments. Our approach also learns offset behaviors for the inconsistency caused due to setbacks without the need to explicitly model the various setbacks that we see in real-world environments, and also learns the importance of multimodal features, which in turn improves the accuracy of terrain adaptation. Thank you, and I'll take questions from the audience now.
Very, very cool. Thanks, Srir. I think we should have time for a couple of quick questions maybe, and let's start from the in-person audience and see if there are questions there.
Hi, Srir. So first of all, thank you for the nice presentation, and I'm very excited to see the robot being brought into the real world and actually being deployed in the wild. So I have a question regarding the intuition behind the fact that the proposed method outperforms the TRAL method, because if I recall correctly, in TRAL, you actually do representation learning and apprenticeship learning at the same time, and to solve the same problem, right? So why this more end-to-end approach as you proposed in this work? So learning kind of like a residual on top of the expected and actual actions, why it can outperform the previous TRAL framework?
Thank you for the question. To answer your question, the difference of our approach in a theoretical level is our approach acts as a closed-loop controller. So it takes the feedback of recent behavior differences. So it sees if the robot is actually being able to produce the expected behaviors or not, and it keeps a track of what the actual behaviors the robots are encountering based on like a SLAM-based method. So if the robot is able to encounter, if the robot encounters wheel slips, our approach is aware of that. So just because our approach has this closed loop capability, it's able to outperform the TRL approach. So when we see the TRL approach, the way it works is it's an open loop controller where it just sees the terrain in front of it, and then it just executes the navigational behaviors. However, it does not have a feedback on how it is performing. So that's the main difference between these two approaches, and this is the main reason why we observe and performance improve.
Okay, thank you.
Maybe a quick follow-up before we move on to the next question. A quick follow-up on that. Since you're mentioning feedback control and so on, is there any connection with traditional techniques for control theory, adaptive control or things like that?
The control is kind of an adaptive control, but the gains are fixed, like if we are just comparing the learning. But however, what we try to do here is we take, so the first expected behavior generation is based on representation learning. So it just uses representations of the camera images that the robot has got. So, but in terms of learning, the adaptive control, it's just learning from representation again and seeing which of the behavior differences are the most important to try to suggest how to go forward. For example, if we take the difference from SLAM-based methods for a robot like Husky, just because we can control only 2 degrees of freedom with this robot, there are going to be certain behavior differences that are not going to be important. So with learning, we are trying to figure out which are the ones which are most important, and we ask the robot to automatically figure it out. So
understood. Okay.
Yeah.
Thanks. Let's see if there is one final question from the audience, and then we'll need to wrap up.
I don't think there are any live audience questions.
All right. Thanks. Okay. So at this point, thanks again, Sriram, for the presentation, and I will pass it back to Lel for the closing.